Dear students, in physics in the section measuring instruments, now we are going to see the second experiment. Before this, what did we see? We saw vernier caliper. In the first experiment, we saw vernier caliper, how to use vernier caliper. You remember vernier caliper had a better accuracy than the measurements we take from the meter ruler. Because meter ruler, the least count is usually 1 millimeter. Anything smaller than 1 millimeter, we can't measure. Any parts of 1 millimeter, for example, if you have 15.6 millimeter, 15 millimeter you can measure, or 16 millimeter you can measure. 15.6 you cannot measure using a meter ruler. Whereas compared to that, the vernier caliper had a better accuracy because it had usually 0.1 millimeter least count. So 15.6 millimeter was able to be measured using the vernier caliper. But remember, when we were discussing the past paper questions, there was one question that says the manufacturer has indicated the width of the diameter of a wire is 0.18 millimeter. Can you verify this using the vernier caliper? And we said no, because 0.1 millimeter is the least count of vernier caliper. So you can measure 0.1, 0.2, but not anything in between that. So 0.18 millimeter cannot be verified by a vernier caliper. To answer that issue, now we are coming up with another instrument to measure, which is micrometer screw gauge. Usually micrometer screw gauge has least count 0.01 millimeter, right, to the second decimal of millimeters or to the third decimal of centimeters, you will be able to take measurements in micrometer screw gauge usually, because you know, instrument to instrument they can change the least count, they can change the number of divisions in the vernier scale, right? So the least count is not a fixed value. So what I am telling now is the common scenario. So one standard sentence we can say, standard statement we can say, micrometer screw gauge has smaller least count than that of vernier caliper. So length measurements when we take with micrometer screw gauge, that is more accurate than that we take from vernier caliper. So this experiment is all about familiarizing ourselves with micrometer screw gauge and to see like how to get the measurements, right? Still, there are certain disadvantages of micrometer screw gauge as well. For example, you remember in vernier caliper, we had external jaws, internal jaws, and the depth measuring probe, depth probe or depth rod, right? Here, the internal jaws are not there. For example, with internal jaws in vernier caliper, what did we do? We could measure the internal diameter of, let's say, a PVC tube or a hollow cylinder. How to measure the internal diameter? The internal jaws were helpful. That we can do with micrometer screw gauge also. In micrometer screw gauge, you can do everything that you did with external jaws of the vernier caliper, right? For example, measuring the external diameter of a cylinder, measuring the external diameter of a sphere, a ball, measuring the thickness of a, let's say, a glass slide, micrometer slide, right, or the microscope slide. So you can measure the thickness of it. All that you did with the external jaws in the vernier caliper. So whatever you did with external jaws in vernier caliper can be done here with a better accuracy. Whatever you did with internal jaws in vernier caliper cannot be done here. Whatever you did with the depth measuring probe there cannot be done here. Right, so there are advantages, disadvantages. Advantages, it is more accurate. Disadvantage is certain applications of vernier caliper is not possible with this one, right? So let's have a look at this. Now look at the parts and the names. You might have some unfamiliar names here. You need to be familiar with that hereafter, right? See, this is where we are going to keep the object that you want to measure, right? Say you want to measure the thickness of a wooden block, you keep it here. You remember in vernier caliper, If you look at the external jaws, one jaw was fixed, one jaw was movable. And you bring the jaws closer, when both touch the object, you take the measurement. Same thing here, this is what you call anvil. Anvil, can you see anvil? Anvil is a fixed part, it doesn't move. Anvil is fixed. On the other side, you have spindle. Spindle can move. Spindle can move. Like when we rotate this thimble, when we spin the thimble, spindle can move front and back or in and out. Okay. So by spinning the thimble, we are going to bring it closer and make it contact with the object, and then we take the measurement. But we have to be careful there. We don't usually spin the thimble. There is something called thimble head, a small screw-like thing, a thimble head. Using that only we are going to spin it. When you rotate that, the spindle will move and you bring it close to the object. When anvil and spindle both touch the object, you have to get the measurement. How do we know both touch the object? When you tighten using the thimble head, the moment everything is in touch, the moment anvil, spindle both are in touch with the object, you will hear a tick-tick noise, a tick-tick sound. So when you keep rotating the thimble head, the moment you hear the tick-tick sound, you know, all right, now it has come in contact. Why do we have that? Imagine if that is not there, right? You might tighten this more and it can even result in a deformation of this object. The shape of this object might change. Like you tighten the screw. If you keep on, rotating, there are two problems. One, the object might get deformed. Imagine something like regiform if you want to measure. You tighten it, it gets compressed. Then the measurement you take is not the measurement that actually was. Or if you are measuring the thickness of a glass piece, you tighten it, it might crack. Understand? So, to make sure, okay, we don't deform the object. We keep the object as it is and take the measurement. We have this setup. What is it? Thimble head will give when you rotate the thimble head, the moment spindle touches the object, you will hear tick tick sound. And another reason, like if you tighten, if you over tighten it, the threads here, the lines, the threads, on the threads only the spindle moves, right? The threads might get damaged. So to avoid all that, we have this setup. It has been tested a couple of times in the exam. How do you know the object and spindle are in contact? From the tick-tick sound that you hear. So thimble and thimble head. And on the thimble, can you see there is a scale here? Right? Which is what we call round scale or thimble scale. Right? It will be like this. Look at this. You will have scales like this. Right? If I look it from here, that's how the scales are going to look like. Right? And here, this is what you call sleeve. On the sleeve only this moves. On the sleeve. Sleeve is fixed, but thimble will move. With the thimble, the spindle also will move. So the spindle is inside. When the thimble moves, the spindle also moves. Sleeve remains fixed. Sleeve remains fixed. That's what you call sleeve. On the sleeve, you have main scale. On the sleeve, you have main scale. Clear? So what will happen? Let's say when you rotate this thimble once, this is going to move. The thimble or the thimble scale, right? This we can say round scale or rotational scale or thimble scale, whatever. Thimble scale, right? That's going to move. That's going to move. Say when you do one full rotation, if it moves by 1 millimeter, let's look at this. Let's say this thimble has scale up to 100. Let's say 0, 5, 10. Likewise, it goes up to 95 and then 100. Let's say there are 100 divisions in the circular scale. Circular scale. 100 divisions. When it goes one full rotation, it moves by, let's say, 1 millimeter on the main scale. 1 millimeter on the sleeve it moves, right? Then I can say 100 divisions, when 100 divisions are rotated, it moves by 1 millimeter. This is just an example I am telling. Screw gauge to screw gauge, it can be different. Another one might have only 50 divisions. and it might move 2 millimeter or it might move half a millimeter, then the calculation will be different. Here I am taking an example where the circular scale has 100 divisions and it moves by 1 millimeter on the main scale when one full rotation is made. Then I can say one division is going to be 1 over 100 millimeters. That is 0.01 millimeter. 0.01 millimeter. One division is 0.01 millimeter. Clear? This is what we call least count of this measuring instrument. How do you find the least count? First thing you need to check how many divisions are there in the circular scale. Second thing you should check, one full rotation is made on the thimble, how much it moves, how much the scale moves on the main scale. Right, say for example, if you had another situation like this, okay, 50 divisions are there, it moves 1 millimeter. Then one division is going to be 1 by 50, which will be 0.02 millimeter. Understand? So, you have to ask two questions when you find the least count, the minimum measurable distance using a micrometer screw gauge. First question you ask, how many divisions are there on the circular scale? Second question you ask, when the circular scale rotates by one full round, by how much it moves on the main scale? Divide those two. How much it moves, how many divisions, divide it, then you can understand when circular scale moves by one division, how much it moves. Clear? When I do the experiment, I will show it again with the instrument. So, this is how we find the least count. Clear? Let's go further and see usage of the micrometer screw gauge. Finding the thickness of a microscope slide, that small glass slide we have, you are going to find the thickness of it. Finding the diameter of a steel ball. Steel ball means small, very small balls with like few millimeters, say 3, 4, 5 millimeter diameter. Finding the diameter of that using the micrometer screw gauge. This is what we are going to do. Another thing you may be able to do, finding the thickness of paper. Paper, we don't take one paper, either you fold it and get like 10, 20 folds and put it together, find the thickness, divide by number of folds you had, and then you can find the thickness of one paper. Yeah. So, those are what we are going to do with micrometer screw gauge. Materials and apparatus required, you need a micrometer screw gauge. Obviously, you are going to take the measurement using micrometer screw gauge. A thin wire, the wire's thickness we can take. Microscope slide we can take. Steel ball we can take. Method. Obtain the least count of the micrometer screw gauge. That's what I already explained, how to get the screw gauge least count. Then rotate holding thimble head only until the spindle touches the anvil. So, you rotate it using the thimble head only until the spindle touches the anvil. That means there is nothing in between. There is no object kept in between the anvil and spindle. You rotate the thimble head so that spindle moves and it touches the anvil. Right? When spindle touches the anvil, how do we know? The tick tick noise will be there, tick tick sound will be there. When the spindle touches the anvil or when these two are in contact with any other object, the thimble head would rotate freely, making a ticking sound. That's the important part of it. Ticking sound. Note down any zero error if shown. What is the zero error? See, when you are studying this experiment, make sure you already have studied the previous experiment I have done. Each section, see for example, now we are doing measuring instruments. There are going to be 4 experiments. Then there will be few experiments in mechanics. There will be some more experiments in waves and oscillations. Then you will have light. Light will have 9 or 10 experiments. Then you will have heat. There are few experiments. Then electricity. Section by section, there are going to be a number of experiments in each section. Let's say now measuring instruments, if there are 4 experiments, we will number them 1, 2, 3, 4. When you are learning the third experiment, you should have already studied the first and second experiment before coming to the third one. Why? There are certain things that we explain in the first experiment, we will not spend much time explaining it again in the second experiment. So it's a cumulative knowledge that goes forward. So you did not learn the first experiment, you suddenly come to the second experiment. Certain things I mentioned here may not be understandable to you simply because you did not learn the first experiment. So every section you study in the order that we do experiment. See, later also, let's say there are 6 experiments in electricity. You have to go in the order. First you learn the first experiment, then the second one, third one, fourth one, fifth one. So please study in the order that we do experiments. We have numbered the experiments in the right order. You learn it in the right order. Right. Coming back here. So I said zero error, we have done it in the vernier caliper also. What did we do? We brought the jaws together. When both jaws were in contact, you check vernier scales 0 and main scales 0 should be aligned, should be coinciding. If vernier 0 and main scale 0 are not coinciding, then you call it there is a 0 error. Right? If vernier has moved more inwards, you call it a negative 0 error. If vernier has yet more to move but still jaws are already aligned, then you call it positive 0 error. I have done this already. A similar issue could be here also. But you rotate the thimble head, move the spindle goes and touches with anvil. When that touches with anvil, actually the 0 of circular scale and the 0 of main scale should be aligned, should be coinciding. If it is not coinciding, there is going to be a 0 error. Let me show it to you. Look at this. Let's try to understand the 0 error first. Right. Let's say this is the main scale line. You will have 0, 1, 2, 3, 4, again 5, 6, likewise it will go on. 0, 5. Sometimes some main scales will have half marks also. 0, half, 1, 1.5, 2, half they mark down. I didn't mark half here. Okay. Now I am drawing the thimble or circular scale little bigger so that you can observe it clearly. Right. Right. Look at this. When both anvil and spindle touch, can you see the 0 line here? The main scale 0 and this 0. This is the vernier 0 or the circular scale 0. This is how it should be. If this is how you have it, then there is no 0 error. Can you see? This line is exactly at the 0 of the main scale. Also, the circular scale 0 is aligned with the main line. If it is like this, it has no 0 error. No 0 error. Understand? Right. The numbers will be like this. 1 is here, 2, 3, 4, 5. So here it is going to be 99. If it is 100 divisions, 99, 98, 97, 96, 95. Understand? This is how it has to be. So you move it anti-clockwise. If you want to open the gap between anvil and spindle, you have to move it or you have to rotate it anti-clockwise. It has to be moved this way. So from 0 to 1 it moves. There is a small gap between anvil and spindle. 2, 3, 4, likewise keep rotating anti-clockwise, it opens. Rotated clockwise, it closes, the gap closes. So when the gap is fully closed, the 0 of circular scale should come like this, right? The main scale 0 and the circular scale, they are aligned. Not only that, 0 of circular scale must be on this horizontal line. But sometimes we may not have that, it's an error. You remember the example I told you about the weighing scale, the electronic weighing scale. If you don't keep anything on it, it has to show you 0 grams. But sometimes there can be an error, it might show you 5 grams, 6 grams. Or it might even show you minus 5 grams, minus 3 grams it shows. Right, but electronic scale, it's very simple. There's a button, you press that, it makes it 0 immediately. But here we don't have any buttons. So if the error is there, it's error for always, error forever. So that error has to be calculated and always it has to be adjusted. So let me show you how the error is going to be. Look at this situation. Main scale 0, 1, 2, 3, 4, 5, 0 and 5, right? Look at the thimble or the rotational or the circular scale. You have it like this. Have it like this, where zero is here. Line number 3 is the one that comes here. 5 is here. So actually there is a little more space for us to rotate and bring this 0 up there. But before that, the thimble head started making ticking noise. That means before it goes to 0, it started making the ticking noise. Which means when the spindle and anvil are touching, it already shows you a reading of 3. 3 means what? Right? 0 and 3 means, right? The error here is 3 circular scales. One circular scale is 0.01. So 0.03 millimeter error is there in this case. 0.0 millimeter, 0.03 millimeter error. Is it a positive error or negative error? Imagine when I want to keep something in between anvil and spindle, I have to rotate it anti-clockwise. So from 3 only it's going to, like when I rotate it anti-clockwise, next I will have 4 here, 5 here, 6 here. So let's say, okay, when I get the measurement, it comes as 25.3 millimeter. Already it started from 0.03 millimeter only. Like in the weighing scales example, it starts from 5 gram. That means when you kept nothing on it, it shows you 5 gram. Then when you keep the object, it shows you 100 gram. What's the actual weight of the object that you kept? It's not 100 gram. Because from 5 gram, it has gone to 100 grams. Means 95 gram is the correct weight of it. 95 gram is the correct weight of it. A similar situation here. It starts from 0.03 millimeter and it goes further. So if you want to get the actual value from the reading, you have to subtract this. That's what we call positive error. Positive 0 error. Positive 0 error. So if you have a situation like this, you call it positive 0 error. Then how would be negative 0 error? Negative 0 error will be like this. Look at this. Zero, 1, 2, 3, 4, 5. That's main scale. It goes on like that. I'm marking only up to 5. See how your thimble scale looks like. Zero is here, 95 is here. So what does this mean? 0 should have stopped at this point, but it has gone further. It has gone into the negative side. Right? It should have stopped at one point, but it has gone more into the other side. By how much? Here you can see by 3 divisions. Actually, what is tallying here? 97. 97th division is here. So here the error is going to be the negative error because 0 has gone passing the point where it has to stop. Earlier 0 did not reach the point where it has to come. If 0 did not reach the point, you call it positive error. If 0 has gone passing the point where it has to stop, you call it negative error. How much is the error? Out of 100 divisions, 97 divisions are matching here. Out of 100 divisions, 97 divisions are tallying their least count is 0.01. You remember in vernier caliper also, this is how we found the negative error. From the total number of divisions in vernier, we found out how many divisions are aligned there, get the difference, multiply by the least count. Same, if there are 100 divisions in the circular scale, 97 is the one that is being coinciding here. So 100 minus 97 into the least count, 0.03. But this you call it negative zero error. Negative zero error. Positive zero error, deduct from the reading or reduce it from the reading. Deduct it from the reading. Whereas negative error, add with the reading. Add with the reading. Are you clear? Why do we add it? Usually this is the equation, reading minus error. But if it is a negative error, it's going to be reading minus error, it makes it plus. So in terms of value, if you talk, positive error has to be deducted, negative error's value has to be added. Why? Think your weighing scale shows minus 5 gram. Then after you keep the object, it shows 100 gram. So from minus 5, it has gone to 0 and it has reached 100, means altogether 105 grams should have been the change. So the actual value, actual weight of the object you kept is 105 gram. Something like this. It shows at 97. So when you keep an object and move it, from 97 it has to come to 0. So backwards it has to come to 0 means three scales it has to move to come to 0 itself. Then only from 0 it goes further. Right? So from the reading, this error has to be added. If they say negative error, this has to be added. If it is a positive error, it already shows you a reading. On top of that only you are getting the extra reading. So it has to be subtracted. See, this is how we identify the positive error. This is how we identify the negative error. Clear? Right. So whichever the measuring instrument, it can be vernier caliper, it can be micrometer, screw gauge. The first two steps you do, first one is identifying or calculating the least count. Second one is identifying the zero error and calculating it. After that only we go into taking any measurement using that instrument. So that's about the zero error. There are some diagrams. See, 0, 0 must be aligned. Then you say no zero error. If the 0 is yet to reach the other 0, main scale 0 and vernier 0, if this is how you have it, that's a positive 0 error. That's what I have shown here. See, 0, 0, 3. If the 0 of the vernier has gone passing where it has to stop, then you call it negative 0 error. Look at this. Here 0 has gone passing where it has to stop. The main scale's line has been passed by 0. Then you call it negative 0 error. Right. Now we will see how to get the measurements. First one is thin wire. To measure the diameter of the wire, place it between the anvil and the spindle and rotate the thimble head until the wire is held properly between these two. That means like this. See, here let's keep the wire. How do you keep the wire? Right. Keep the wire like that and then keep moving the spindle. You can rotate the thimble head, move the spindle so that it becomes in contact and you hear the tick tick noise. So the wire is like this. Wire is kept like this. Right? And then get the measurement. And how do we get the measurement? The same way that we get the measurement in the vernier caliper. Let me show it to you. How do we get the measurement? Let's say you have a reading like this. look at this. Say the reading is like this. Let's say here you have this is let's say 25, then this is 26, 27, right? Then here you have 45 out of 100. So we are going to write the reading like this. Reading is going to be, in the main scale 27 has been crossed, but not 28. I can't see 28 yet. 27 has been passed. So 27 plus, assuming these are millimeter marks, main scale is in millimeter. 27 plus 45 divisions of circular scale into least count. Least count 0.01, then this will become 27.45 millimeter. That's how you get the reading. You look at the main scale, see what is the last division you have crossed, write that down, and then see which division of the circular scale is in the horizontal line, that into the least count, 27.45 as per my diagram. This is how you get the reading. Obtain the value of the diameter, rotate the wire by 90 degree and obtain reading again. See, now the diameter you have obtained is this one. That's the diameter. Then we will rotate the wire and get the diameter on the other direction also. Because the cross section may not be a uniform circle, right? So to get an average, you take in one direction, rotate it, take it in another direction. Get the average, that's going to be the diameter at this place. Then move the wire, take it at another two places. Do the same operation at another places. So altogether you will have three different values for diameter. See, in one place you take 90 degree, take two values and get the average. So I can make a table like this. Look at this. See, I can make a table like this. How? Position 1, position 2, position 3. Position 1, you will have reading 1 and reading 2. Get these two and get the average. So this is one diameter. Position 2 also get two readings, get the average. Position 3 also get two readings, get the average. And then you have three values for diameter. Get the average of all them. That is the final average diameter of this wire that we have used, right? Then microscope slide, same thing. You remember when we used the glass block and we wanted to measure the thickness of it, what did we do? We measured the thickness at multiple places and we got the average of it. Why did we do that? Because the thickness may not be the same everywhere. It might not be a proper cubic shaped one. There can be, variations. So we did that. Here also arrange the microscope slide to fit between the anvil and the spindle and obtain readings for thickness of the slide in three different places. Get the average of them. Clear? That's about this. Steel ball also same. Steel ball, arrange the ball to fit properly between the anvil and the spindle and obtain the readings for three diameters normal to each other and get the average. Right? So this is how we are going to do the experiment. Now you are familiar with the names of the parts. You are familiar with, the zero error. You are familiar with the least count. Let's take the micrometer screw gauge and see whether we can obtain all these readings. So the apparatus we have, this is the primary one in this experiment. This is what we call micrometer screw gauge. The parts of this and how to use this, I will show you once I start getting the measurements. For the moment, just look at the shape of this. This is what we call micrometer screw gauge. And these are the objects that I am going to measure. Look at the first one, it's a cylindrical shaped pin, a very thin wire or pin. I am going to measure the diameter of that. Diameter might be around 1 millimeter, very small diameter. I am going to measure the diameter using this micrometer screw gauge. And we have a glass slide, a microscope slide, glass slide. I am going to measure the thickness of this slide. Also we have a steel ball. I am going to measure the diameter of this spherical shaped ball. Right, this is what I am going to measure. So you can see like very small measurements I am going to take. So when you take measurements in the range of 1 millimeter, if we can minimize the error that we get, then the percentage error can be minimized. For example, think when you measure 1 millimeter, if you have an error of 0.1 millimeter, that's actually 10% error. Having 10% error in your measurements is not acceptable. It's significant error. Whereas when you get the measurement of 1 millimeter, if you have an error of 0.01 millimeter, that's just 1%. 1% error in your measurements is somewhat acceptable. Right? Mostly at school level experiments, practicals, it is acceptable. 1% error is okay. It's not as significant as having 10% error. So do you understand the importance of measuring with high accuracy? If I measure the thickness of this using the vernier caliper, the error can be 0.1 millimeter because the least count is 0.1, isn't it? So the percentage error will be big. So when you measure smaller and smaller lengths, you need better and better accuracy. So for these measurements, the width of the thickness of this glass slide, the diameter of this pin, the diameter of this steel ball, since they are very small measurements, I want to improve the accuracy. That's why I decided to use micrometer screw gauge. Now let's see how we are going to use this. All right, students. See, I have fixed this micrometer screw gauge on a stand so that you can see the measurements and every operation clearly. Usually when we do this experiment at the laboratory, we don't fix it in the stand. We just keep it in the hand and do it. But here I have fixed it on the stand so that you can see things more clearly. To show it more clearly through the cameras, I have fixed it here. Let's try to understand the parts of this, the names of the parts, because some unfamiliar names are there. We have to become familiar to do the exam properly. Look at this. There is a gap here. In this gap only, I am going to keep the object which I am going to measure. Right? I can increase or decrease this gap. Look at this gap now. See, when I rotate this, can you see this gap is increasing? This gap is increasing. Similarly, when I rotate it on the other side, the gap is decreasing. So in this gap only, I am going to keep whatever that I am going to measure. This part is what we call anvil. Anvil. See, one side of this gap. But this is fixed. This doesn't move. Anvil doesn't move. On the other side, when I rotate this head, the moving part here, that's what we call spindle. Spindle. Right? This is what we call spindle. Can you see this one? Right? There is some scale marked here. When I rotate, that also rotates. That's what you call thimble. 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 And this handle is what you call thimble head. See, what I hold to rotate, we call it thimble head. We should avoid holding here and rotating it. When I progress with the experiment, I will tell you why we should not rotate from here. Usually we hold this thimble head and using that only we rotate it. Right? In vernier also I have told you, first when you start using a measuring equipment, first thing try to understand the least count. Find the least count of that equipment. 2, check whether there are any zero errors. 3 is taking the measurement. So now let me see the least count. How much is the least count in this? First understand, look at the main scale. This is what we call main scale. In the main scale, this is 0. And the next line, this is 1. This is 2. 3, 4, 5. The next big line is 5. And can you see below this horizontal line, there are some more lines. They give you the half of a millimeter. For example, look at the first one. Okay, come again. This is 0. And this first line below here, that's 0.5 millimeters. Up, this is 1 millimeter. 1.5. 2. 2.5. 3. 3.5. 4. 4.55. That's how it goes. It goes up to 2.5 millimeters maximum. 2.5 millimeter, 2.25 millimeters maximum, 25. Come again, 0, 0.5, 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, 5. Likewise, it goes on. So, in the main scale, you can measure 0.5 millimeters, 0.5 millimeters. That's what the main scale is. And can you see we have another circular scale here? You can even call it circular vernier scale. Let's try to understand that. Let me bring it close to this 10th mark. Right. Can you see now? The 0 of the circular scale is in line with this horizontal line. And now, this circular scale is aligned with 10 millimeter line on the main scale. 10 millimeter on the main scale and the circular scale, they are aligned. Now, let me rotate one full round and see what happens. See, I am rotating one full round. See, you can see it was at 0. Now, this is 5, 10, 15, 20, 25, 30, 35, 40, 45. Again 0 comes means 50. So, there are 50 sections, 50 parts in the main scale, in the circular scale. So, when I rotated all those 50, that means one full round is rotated. See, earlier it was with 10 millimeter line on the main scale. Now, can you see it has come to 10.5 millimeter. 10.5 millimeter. Let me rotate once more. Slowly one full round, one full round. Again, when I see 0, I'll stop it. Right. So, again when I rotated, it was earlier at 10.5, now it has come to 11 millimeter, 11 millimeter. So, first time when I rotated from 10 millimeter, it came to 10.5. Again when I rotated, it came from 10.5 to 11 millimeter. That means one full rotation moves on the main scale by 0.5 millimeters. That's what we call pitch. So, the pitch is 0.5 millimeter. When one full rotation happens on the circular scale, on the main scale it moves by 0.5 millimeters. And circular scale has 50 sections in it, 50 parts in it. 0.5 millimeter it moves, 50 parts are there, divided 0.5 divided by 50, that is 0.01 millimeter is the least count of this micrometer screw gauge. This is how we find it. What's the pitch? What's the number of sections in the circular scale? You divide it. Pitch means when you do one full rotation of the circular scale, how much it moves on the main scale? 0.5 millimeter. Number of sections 50. Divided 0.01 is the least count. So, that's the smallest thickness we can measure using this micrometer screw gauge. Clear? Least count is sorted. Now, let us check whether there is a 0 error, 0 error. 0 error, I have to rotate it until these two touch each other. Anvil and the spindle until they touch each other. Until this gap is closed, I have to roll this. You can see the gap reduces. When the gap becomes almost 0, concentrate, you will hear some sound. See, it's going to be 0, the gap is almost 0, now concentrate. Did you hear that ticking noise or ticking sound? Right? Come again, we will do it once again. Okay, I open this, let me close it. Concentrate. Right, that's what we call ticking sound. So, what happens is, when the anvil and the spindle touch each other, then the ticking noises or ticking sound is generated. That means, after that when you rotate the thimble head, the spindle does not move in. So that the equipment is protected. What will happen if you hold this and if you rotate is, even after they have touched, even after the anvil and the spindle have come in contact, you wouldn't know that they have come in contact. You might still try to rotate this. That might damage the screw here. Right? That might damage the equipment. So it might not give you precise readings next time when you are using it. So to protect the equipment, we use this thimble head. So precisely when it touches, it gives you the ticking sound, so that you have to stop rolling it, stop rotating it. Understand? So they asked you in the exam, why do we have to move the spindle using the thimble head? Why not thimble? Because when you use the thimble head only, when the gap is closed, the ticking sound is generated, then you know, okay, we have to stop rotating it now. So that you can protect the equipment. Otherwise, the screw will be affected, it will be damaged. Right. Now look at this, when the gap is closed, when I hear the ticking sound, the zero of this circular scale has to be aligned, has to be in line with this horizontal line. Can you see the horizontal line? It's more or less same, right? There's a small gap which we can't measure in this. So, zero of the circular scale and horizontal line of the main scale are almost aligned, which means this doesn't have a zero error. This doesn't have a zero error. Suppose, now I am going to take a different case and show you positive error and negative error. Suppose when the ticking sound is heard, if this is how you had it, okay, if this is how you had it, now the zero is not in line with the horizontal line, right? Which section is in line with the horizontal line? 1, 2, 3, 4. Fourth section of the circular scale is in line with the horizontal line. 4 sections means 4 into least count 0.01. So, 0.04 millimeter error is there. And it is a positive error. How do we know positive error? See, it has not passed the 0 yet. So, when I was rotating it, when it closed, if it has gone passing the 0 also, if the circular scale has gone passing the 0 also, that means it has gone to the minus side of it, then we call it negative error. But now it has not gone passing 0, it is still on the right side of 0. It is still on the right side of 0. That means it is still on the positive side of 0. Then we call it positive error. Positive error. So here we have a positive 0 error, like the one I have shown now is positive 0 error of 0.04 millimeter. So after getting the reading, we have to subtract this value to get the exact measurement. Remember, in vernier also I explained you, suppose you have a weighing scale, sometimes a digital weighing scale, sometimes due to some error, initially it might not be at 0. It might be at 5 grams. When you kept nothing on it, it might show 5 grams. After that you keep an object. Now if it shows 50 grams, the actual weight of the object that you have kept is not 50, because it has gone from 5 grams to 50 grams, which means 45 grams should be the weight of it. So from the reading, you have to measure the initial 0 error to get the actual measurement. A similar thing is here, positive 0 error if we have a situation like this. That means when the ticking sound is heard, the 0 of circular scale is not aligned with the horizontal line of the main scale. Also, the circular scale has not gone crossing 0. It is still on the right side of the 0. Then you call it positive error. Let me show you negative error. I can't show negative error on this because negative error has to go passing 0. It doesn't go in this. Let me take another line as 0. Look at this. Right. Let's assume this 5 millimeter line as 0 for now. Just assume that. Just assume 5 millimeter line as 0. Okay. Then, look at this carefully. This is a situation where there is no 0 error, because 0 of the circular scale is aligned with the horizontal line. This is the case with positive error. How many sections? 4 millimeter, 4 sections. That means 4 into least count 0.01. 0.01 is 0.04. 0.04 millimeter, positive error, positive 0 error. Now look at this. Now the line goes crossing the line. Can you see? This is how it has to stop. This is where the perfect condition, no 0 error. This is how it has to stop. But if it has gone like this, now look at this. That means it has gone passing the 0 line also. Then we call it negative 0 error. How many sections? 45 is getting aligned with this line. 45 is aligned means for a negative 0 error, you have to subtract that from the total sections. There are 50 sections altogether. Now 45 is aligned. That means 5 sections have gone passing 0. 5 sections, see, 0, 45. So there are 5 sections. 5 sections means 5 into 0.01. 0.05 millimeter is the 0 error, but negative 0 error because 0 has gone passing it. Understand? This will be negative 0 error. Negative 0 error means, imagine the weighing scale. Initially it shows minus 5 grams. Then you keep an object, now it shows 50 grams. So what's the weight of the object that you have kept? From minus 5 it has to come to 0. And then it has gone to 50. Altogether 55 gram has to be the measurement, isn't it? So the reading was 50, error was minus 5, but the actual value is 55. A similar situation. You have minus 0.05 as your error. So once you get the reading, this absolute value of 0.05 has to be added. Suppose you get a reading of, let's say, 5 millimeters. With that 5 millimeter, this 0.05 has to be added. So negative error means, now this is the formula, reading minus error. Reading minus error is the measurement. Reading minus, if it is positive error, let's say positive error of 0.04, reading minus 0.04, that's it. But if it is negative error, reading minus 0.05. Reading minus 0.05, 2 minuses back to back makes it plus. So that will become reading plus 0.05, right? So a minus error, the value will be added to the reading to get the actual value of it. Be familiar with these kind of adjustments. But here in our apparatus, right, see when it is at 0, let's see again, right, when you hear the ticking noise, you can see zeros are almost aligned. 0 here and the horizontal line here are almost aligned. There is a small gap which we can't measure. That's almost 0. That's almost 0. That means there is no 0 error. Now let me show you how I am going to get the measurements. First I am going to take this pin. First I am going to take this pin and I am going to get the diameter of this pin. Diameter. So what do we do? Open the gap here, the gap between anvil and spindle. Open it. Keep the pin in the middle. Close the gap. See? Repeat. I keep it. When I close it, you can hear the sound again. See? See? Right. When you hear the ticking sound, stop rotating it. Get the measurements. Look at the measurements. 0, 1. It has passed 1 millimeter, but it has not passed 1.5 millimeter. Look at the circular scale. 20, 21, 22, 23. 23 is coinciding with this. That means coinciding with the horizontal line. 23 sections means 23 into 0.01 is 0.23. 1 millimeter has been passed. So 1 millimeter plus 0.23 millimeter. 1.23 millimeter is the thickness I am getting. To get precise reading, what do we do? Again, loosen this, rotate this by 90 degree. See, rotate the pin by 90 degree, right. Rotate the pin by 90 degree. Again, tighten it. Again, tighten it until you hear the ticking sound. Check this now. 1 millimeter has been passed. 20, 21, 22, 23. Again we get 23 millimeter in the circular scale. 23 sections. 23 sections means 0.23 millimeter. 1.23 millimeter is the reading. 1 millimeter on the main scale, 0.23 millimeter on the circular scale. I have taken the measurements at this point of the pin, right? You can take at different points. Let me take at another point. See? Okay, at this point. Ticking sound. Get the readings. 1 millimeter has been passed. Again, 23 is what coincides with the horizontal line. 23 into least count, 0.01. So 0.23. 1 millimeter on the main scale. Answer is 1.23 millimeter. Again, rotate this by 90 degree. Loosen this. Rotate by 90 degree. Get the reading. Because the thickness, the diameter might vary slightly. So if this is the cross section, or let's say if this pencil is the cross section, you get the diameter this direction and again get the diameter in this direction. Right? If this is the pin, you get the diameter in this direction. You get the diameter in this direction. And then again you get the diameter in the other direction. Two perpendicular directions you get the diameter, because sometimes the diameter might slightly vary. Because of that we get the measurement like that. So here I rotated again. Now check. Still we have the same reading. 1 millimeter on the main scale, 23 on the circular scale. So 1.23 millimeter is the reading. Right? So you can get it at multiple points of this pin and get the average of all of them. Be careful when you get the average. 0.01 is the least count of this apparatus we are using. So after getting the average, you have round it to second decimal and give the answer. Suppose you get the average in 3 decimals, you can't give it in 3 decimals because you are using an equipment which has 0.01 as its least count. So all the answers have to be rounded to 0.01 and give when you get the average. Right? So you get the measurements at multiple points, get the average, round it to 2 decimal points and give the answer. Similarly, let me get the thickness of this glass slide. The glass slide. Let me check the thickness of this. Thickness. Open it. Keep it in between the anvil and spindle. Close it. See, you can hear that ticking sound. Stop there. Let's get the measurement now. You can see 1 millimeter and this 0 is almost aligned with the horizontal line. 0 almost, 0 of the circular scale almost aligned with the horizontal line. So we can say 1 millimeter is the reading. On the main scale 1 millimeter and there is no reading on the circular scale. No reading on the circular scale. That means 1 millimeter is the reading. Take it at multiple points. Let me take it another point here. Ticking sound. 1 millimeter on the main scale and no reading, 0 reading on the circular scale. Can you see? 0 is almost aligned with the horizontal line. We will take it at another point. At this point, 1 millimeter on the main scale. On the circular scale, I can see one first section coincides with the horizontal line. Right? One section here, one part. One part means 0.01 millimeter. So 1 millimeter on the main scale, 0.01 on the circular scale, 1.01 has to be the answer. So I got 3 readings, 1 millimeter, 1.01. If you get the average, 1 plus 1.01 divided by 3, you will get 1.003. But I can give the answer in 2 decimals, 3 decimals, round it to 2 decimals, that will become 1.00 itself. 1.00 itself. So the thickness of this glass slide I am using is 1.00 millimeter. Are you clear? So after you have found the least count, after you have found the 0 error, getting the measurements is very simple, very simple. And this equipment particularly doesn't have any 0 error. So answer the reading I am getting is the actual measurement as well. I don't have to do any adjustments on it. Next, let's keep this steel ball and get the thickness or get the diameter. Let's use this steel ball and get the diameter of this. Let me widen the gap between anvil and the spindle. I need more. Right, keep it in the middle, close the gap until you hear the ticking sound. There you go, the ticking sound. Get the readings. You can see on the main scale 6 millimeter has been passed, 6.5 millimeter not yet passed. So 6 millimeter crossed. Take the circular scale 34, 30, 35, 34. 34 sections means 0.34 millimeter. In this one, in this equipment 0.01 is the least count. 34 sections means 0.34 millimeter. 6 on the main scale, 0.34 on the vernier scale, 6.34 millimeter. 6.34 millimeter. Again, rotate this by 90 degree and get it from another point, another angle. Loosen this. Right, I rotated that. We still get the same reading. Can you see? 6 millimeter on the main scale, 6 millimeter on the main scale, 34 on the circular scale. So 6.34 millimeter is the diameter. Likewise, you can get it at multiple points, get the average. That would be the diameter of this steel ball. Clear? So that's how we use a micrometer screw gauge to get the measurements. Vernier, we had some other usage as well, getting the internal diameter, depth. Those measurements we can't get from the micrometer screw gauge. We can measure only the external diameter, only the external diameter. Internal diameter, we don't have the jaws to get the internal diameter here, only the external diameter. Maximum length we can measure is also less. Maximum it can be opened up to 2.5 centimeters, 25 millimeter. Whereas what we had there, the vernier, it can open up to 15 centimeter. But 15 centimeter is there, but still the accuracy is less. It can measure, the least count is 0.1 millimeter. This has 0.01 millimeter. Understand? So it gives you more precise, more accurate measurements. Particularly when you measure smaller measurements, smaller lengths, you need to have a high accuracy, high precision, so that percentage error can be minimized. Then this kind of equipments become very useful. Clear? Right. So go through this, you will be able to answer all the questions that come on this. Again, I repeat, there are 3 points that you need to remember in getting the measurements: least count, zero error, and then getting the measurement. I have shown all 3 clearly with this. Right? Practice this, go through this very well. We will meet up again with another measuring equipment. Okay, students. Now, in this particular experiment, that is how to use the micrometer screw gauge. Regarding this, whatever the structured essay type questions you have got in the past exams, we are going to see. So, this is the first one. I have taken 1990 paper. The diagram shows a part of micrometer screw gauge. It is not drawn to the scale. This gauge has 50 divisions in its thimble scale, and this thimble moves by 1 division, that is 0.5 millimeter in sleeve scale, when it is rotated by 1 full round. So it has 50 scales in it, 50, and it moves by 0.5 millimeter when 1 full round is rotated. What is the least count of this instrument? Least count. It moves by 0.5 millimeter when 50 divisions are rotated. 0.01 millimeter. 0.01 millimeter. When taking measurements, the part marked by A is used for an important function. What is that function? This is the thimble head, or you can say ratchet. What do we use it for? By rotating that only, we are going to move the spindle, right? To move the spindle and make it touch the object, we are going to use that. To move the spindle, simple as that. When carrying out the function in B1, how will you ensure that the ratchet has been used correctly? When the spindle touches the object, it gives you a ticking sound. Then if you get the ticking sound, you know, okay, you have used it appropriately. Let's write it. When spindle touches the object, it makes a tick sound. How will you determine the zero error of this gauge, if any? See, very fundamental basic questions they ask. So how do you find this? Move the spindle until it touches the anvil, right? When anvil and spindle are in touch, check whether the zero of the circular scale or thimble scale is aligned with the main scale's zero. Move the spindle until it touches the anvil. Check whether zero of the thimble scale coincides with zero of the main scale. Zero of the main scale. If not, there is a zero error. If not, there is a zero error. The above diagram shows the reading when the screw gauge is used to measure the diameter of a steel ball. If the gauge does not have zero error, what is the diameter of the ball? Let's go back to the diagram. So this is half a millimeter, 1 millimeter, 1.5, 2, 2.5. 2.5 millimeters passed, 2.5 millimeters passed, and 15th division of the thimble scale is coinciding with the line. So 2.5 millimeter plus 15 scale, that is 2.65 millimeters. 2.65 millimeters. Micrometer screw gauge is most suited to measure the diameter of a thin wire. State the main reason for this. The main reason is this. The diameter of thin wire is going to be in the second decimal of millimeters, like 0.15, 0.17, 0.18 likewise. Micrometer screw gauge is the only instrument that we have in our syllabus. Compared to vernier, this has the accuracy to measure it. Because if it is vernier caliper, it doesn't have the accuracy to measure in the second decimal, right? So let's write it. The diameter of a thin wire has to be measured with 0.01 millimeter accuracy, since it is too small. Micrometer screw gauge has the required accuracy. How will you obtain a good value for the diameter of a sonometer wire using micrometer screw gauge? See, some of you might not know what sonometer is. When we do the section waves and oscillations, we will be discussing about sonometer. Simply for the moment, you can think it's a simplified instrument like a violin. There's a box, a wooden box. On top of that, there are two, bridges, like two wooden pieces. Above the wooden pieces, see, it's like this. This is the box. Then you will have wooden pieces like this. And then on top of that, a wire goes, or a string goes. Right, it's fixed on both sides. So this is what we call sonometer wire. Right, to analyze the behavior of waves and to understand the connection between frequency, wave speed and all that, we use this instrument in a section called waves and oscillation. We will be doing few practicals, few experiments with this as well. Now thing is, why they are talking about that here, this string or this wire, how are you going to find the diameter of this? So this you can't remove it and take it, you can't cut a piece and take it, but no problem, you can keep it as it is, bring the micrometer screw gauge, keep it at different places and get the measurement, simple as that. Each place you may be able to, rotate the angle and get couple of diameter measurements as well. So go to this point, at this point get two different diameter measurements, get the average. Go to this point, again get to here and then get the average of all of them, right? So let's say measure the diameter perpendicular to the wire. Why I say perpendicular is when the wire is like this, you can't keep the micrometer screw gauge like this and get the diameter. It has to be kept perpendicularly. Then only you are measuring the diameter. Perpendicular to the wire at different places of the wire. The average will give its diameter. Right? Give two other measurements that can be measured using vernier caliper but not using the micrometer screw gauge. I have told this repeatedly. Internal diameter can be measured using the vernier caliper but not using the micrometer screw gauge. Also the depth, right? So let's write internal diameter or inner diameter. Second one, depth. That's all in that paper, 1990, that's all they asked. Very straightforward, simple questions. Everyone who knows the equipment can answer this question. Now move on to another one. This is 1998. You are given suitable measuring instruments and a piece of light string to determine the density of a metal ball of about 100 grams. This metal ball has a permanently fixed hook made of the same metal. It's like this. You have the ball with a hook on it. Hook is permanently fixed. You can't remove it. If you can obtain a spring balance set with ranges of 75 gram, 150 gram, 200 gram and 500 gram, which one will you choose for measurement of mass? See, this is about 100 grams, right? So obviously 75 is not enough. 75 is not enough. You have to take something above 100 gram. 150, 200, 500, which is better? 150 is better because it will have high sensitivity, right? Because you want to measure 100 grams. So rather than taking a 500 gram spring, if you take a 150 gram spring, it will have high sensitivity. What is the meaning of high sensitivity? Even for small changes, even for 1 gram change, it will show a significant movement in its index. Say if you take a 5 kilogram string, 5 kilogram spring balance, there a gram of change wouldn't have much impact on the index, right? So try to keep the range as short as possible so that you will have sufficient sensitivity. So let's say 150 gram is suited. They are asking the reason. It will have higher sensitivity. Right, but why not 75 gram? 75 gram will have even better sensitivity, but it doesn't have enough range. You have to measure 100 grams, 75 gram wouldn't be enough for it. Next, a student doing this experiment correctly obtained the following measurements for the diameter of the ball: 3.523 centimeter, 3.519 centimeter, 551, 542, 521. State the reason for variations in these readings. The metal ball might not be uniform. Means what? If you get the measurements at different directions, different positions, it might not have the same diameter. Because it's not uniform, it's not a proper sphere. It is slightly, non-uniform. That's the reason you have different readings. So let's write that. State the reason for the variations in these readings. The metal ball is not a uniform sphere. Not a uniform sphere. If the student has chosen a suitable instrument to measure the diameter, which instrument would he have chosen? Look at this, he has measured up to 0.001 centimeter. In millimeters, if I say it's 0.01 millimeter. Which instrument has accuracy up to 0.01 millimeter? Not the vernier caliper. It's usually the screw gauge, micrometer screw gauge that has this accuracy. Let's write it. Must be micrometer screw gauge. Micrometer screw gauge. Considering the fluctuations in the above readings, suggest another measuring instrument with better accuracy to measure diameter. Give reasons for your choice. Considering the fluctuations. Now look at the values. 3.523, 3.519, 551, 542, 521. Can you see? In the second decimal itself, the variation starts. So, significant variations are there. Since second decimal itself there is variation, you don't actually need this much of accuracy. Even vernier caliper can be used here because vernier caliper can measure up to the second decimal of centimeter. Suppose if we got the values like this, say 3.551, 3.550, 3.553. If this is how we have got the values, if you use the vernier caliper, that wouldn't show you any variation because vernier caliper is going to always show 3.555555. So if these are the readings, then vernier caliper is not suited. But this one, since we have the changes or fluctuations in the second decimal itself, even vernier caliper would have been used here. So that's what they are asking here. Instrument vernier caliper. Variations in readings exist in second decimal point, second decimal of centimeter. Right. Write a formula for density if the mass of the ball and hook is m and the ball's diameter is d. Assume that the mass of hook is m by 50. So you can say d equals mass. Full mass is m. Of that 1/50th is the hook. So the ball has to be balanced. 49 m over 50 divided by volume 4 by 3 pi r cube. We don't have r. D by 2 cube. D is the diameter, right? We don't have the radius. So you solve it. 49 m 50 4 pi d cube. 3 goes up, 2 cube goes up. So here 8 4 2 25. 3 into 49 147 m 25 pi d cubed. 25 pi d cubed. If you are given suitable measuring cylinder and water, mention the main steps of an alternative method to find the volume of ball. What's the meaning of measuring cylinder? You will have a cylinder with uniform cross section and you will have scale here, centimeters, right? So what we will do, we will first fill the water to a certain level and get the reading number 1. Then you drop the metal ball inside this with the hook itself. So what will happen when this is immersed, when the metal ball is immersed into the water, same volume of water has to be displaced, which means the water level will go up. Let's say it goes up here, reading number 2. So this excess water you have got, the change in the reading is because of the displaced water. So if you can find that volume change, that is going to be the same volume as of this metal ball that we have immersed into the water. Let's write it. Fill the cylinder with a certain amount of water, not fully, because if you pour it fully, then when you drop the ball into that, the water will spill out. Then you won't be able to measure how much of water has been displaced. So don't fill it up to the brim, you fill it somewhere in the middle. That's why I say fill the cylinder with a certain amount of water and obtain the reading of water level. Then what do you do? Immerse the metal ball into the water fully and get the reading again. That's all the experimental procedure. Then the calculation would be to find the difference in readings. That will give you the height, find the cross section, internal cross section, multiply. Usually they might have marked it in milliliters itself. So you know you don't have to even multiply everything. The milliliter, say, let's say it's 100 milliliter here, then 125 milliliter here, then you know 25 milliliter is the displaced amount. Right? When you say measuring cylinder, it's usually marked in milliliters. So you can find the excess reading, the difference in readings is the displaced water's volume. Displaced water's volume has to be the same volume as of the immersed object, which is the ball, metal ball. If the scale of the measuring cylinder can be read with sufficient accuracy, give two benefits of method in F compared to the method in B. That means this method, immersing into the water and measuring the displaced water's volume. This method, what are the advantages of this method compared to the other method? What is the other method? We measure the diameter. Problem is, if it is a non-uniform sphere, finding the diameter, even though you get it at 5 points and you get the average, it is still not accurate because the shape is not a perfect sphere, not a uniform sphere. That can be one problem. So compared to that, this will give, because this doesn't matter whatever the shape it is. Even if it is a non-defined space, undefined shape, doesn't matter, still it's going to give you the same volume. So this method is good in that means. Second one, suppose if there are certain cracks, a small crack in the ball, when you find the diameter and multiply, you are going to ignore that crack, right? Whereas here, when you immerse it in water, that crack will not be factored because water will fill into that crack. So water will not be displaced for that particular volume, right? Imagine if this is how you have it. Let's say you have a crack like this. So when you take the 4/3 pi r cube, you basically assume this also to be metal. But when you immerse it in water, what happens? Water will go into this gap and fill it. So this gap will not displace any water. So you will precisely find the volume of metal substance that is there. Let's write down advantage number 1. If the ball is not a perfect sphere, this will give accurate volume. This will give accurate volume. Second one, if there are cracks on the metal, cracks on the ball, this will give accurate volume. Clear? Next one. Right, so this is a question from 2004 paper on micrometer screw gauge. Name the parts of the micrometer screw gauge labeled as A, B, C and D in figure 1. A is what you call sleeve, right? This one, sleeve. A is the sleeve. B is the scale here, right? Thimble scale or circular scale you can say. Thimble scale. C is the thimble. C is the thimble. D is the thimble head or ratchet. thimble head or ratchet, you can see thimble head or ratchet. What is the least count of the above micrometer screw gauge in millimeter? Let's see. You can see here it has up to 50 divisions, and then the 0, 1, 2, 3, 4, 5, and then half also marked. So let's assume half a millimeter it moves when 50 divisions are rotated. That means 0.01 millimeter is the least count. 0.01 is the least count. Write down the scale reading for the diameter of the ball shown in figure 1 in millimeter. Now look at this. 5, 5.5, 6 has been crossed on the main scale. 6 millimeter is crossed. Not yet 6.5. So it has to be 6 plus. Check on the circular scale. 45. Yeah, this is 45, 46, up to 48 it has gone, 48, correct? So 6 on the main scale, 48 on the circular scale. It has to be 6 plus 48 into 0.01, 6.48 millimeter, 6.48 millimeter. Figure 2 shows a situation in which the micrometer screw gauge is adjusted to determine the zero error. Right. State the correct value for the diameter of the ball in millimeter. First, let's find the zero error. Zero error. Now look at this. Zero has gone passing where it should stop. So actually we have a negative zero error here. How much is the zero error? Negative zero error. Altogether 50 divisions are there. If you look at it closely here, 46 division is the one matching with, coinciding with 0 into 0.01. So that's going to be 4 into 0.01, 0.04 millimeter. 0.04 millimeter is the error, that's the negative error. Negative error. Because 0 has gone passing where it should stop. Therefore, the diameter has to be, the reading we got was 6.48, with that I would add this value, 6.52 millimeter. 6.52 millimeter. Write down the fractional error of the measurement for the diameter of the ball. Usually we write the least count and the reading. Right. But understand, it can be written the half of the least count also. I'll tell you why. Both are right. This is right or this is right. I'll tell you why. We look at a meter ruler to understand this. Let's say meter ruler, this is the 8 millimeter mark. This is the 9 millimeter mark. Let's say you have something here which is actually at 8.3. But 0.3 mark is not there, so you don't know. You're going to assume it as 8 millimeter. You can either write it as 8 or 9 because your least count is millimeters. So you will write it as 8. How much is there? 8.3, you are writing as 8.3 millimeters there. Then let's say you have something here, 8.5. 8.5 being written as 8 or 9. You might write it as 8 or you might write it as 9. When you write it as 9, how much is there? 0.5 millimeters there. 0.5. Now let's say you have something here, 8.8. So if it is 8.8, you will write it as 9, right? So 8.8 being written as 9, how much is there? 0.2 is there. So if you correctly read it, 0.5, that means when 1 millimeter is your least count, half of that could be the possible error, maximum possible error. But sometimes, that's why I said, this is the appropriate working. The maximum possible error is going to be half of the least count, right? Divided by whatever the reading you get should be the error, fractional error. But even this is accepted because even though it is 8.88, sometimes you might have confusions to find out whether it is close to 9 or close to 8 because it can be very small, right? The gap is very small. So you won't be able to judge whether it is in which side it is. So sometimes there is a chance even 8.88 you might count it as 8. If that happens, then 0.8 millimeter is going to be the error there. right? If that is the situation, rather than taking half of the least count, you can take least count itself in finding the fractional error. That's why this is given right, that is also given right. Different arguments. Next. What is the precaution taken in micrometer screw gauge to avoid overpressing the object? You rotate using the ratchet so that when it touches the object, when the spindle touches the object, it makes ticking sound. Rotate using the thimble head or ratchet so that when the spindle touches the object, it makes tick sound. It makes tick sound. Clear? It makes tick sound. Next. A wire of circular cross section length L 55 centimeter and diameter 4 millimeter. This one, L and 4 millimeter, is fixed to a disc. Okay, this is the disc. Diameter 5 centimeter and thickness 3 millimeter, as shown in figure 3. Magnitudes given in parentheses are approximate values. Okay, these are approximate values. Of the measuring instruments, meter ruler, spherometer, vernier calipers and micrometer screw gauge, write down the most suitable instrument for the measurement of each of the above quantities. L is 55 centimeter. To measure 55 centimeter, vernier caliper won't be enough, micrometer screw gauge won't be enough. You need to go for the meter ruler. Meter ruler. D1. What is D1? D1 is the thickness here. Diameter. Diameter is 4 millimeter. Since it is 4 millimeter, micrometer screw gauge would be the appropriate one. Micrometer screw gauge. D2 is the diameter of the disc, which is 5 centimeter. Vernier caliper is possible with that. Vernier caliper. Five centimeter you can't measure using micrometer screw gauge, and vernier caliper would be enough because 0.1 millimeter is the least count of that. So 5 centimeter is the measurement you are going to take. 5.1, the percentage, 5 centimeter means 500 millimeter. 500 millimeter, 50 millimeter rather, 50 millimeter, 0.1 over 50 is okay. Look at the fractional error, 0.1, 50. So vernier caliper is okay because that's going to give you just how much? 0.2% error. That's fine. Micrometer screw gauge, why did I suggest here? Because you are going to measure 4 millimeter. 4 millimeter, if you go for vernier, 0.1 over 4 is going to be 2.5% error. That's significant. Usually we like to keep the error less than 1%. Therefore, better we will go for 0.01 micrometer screw gauge. Then what will happen? You will have only 0.25% error. That's fine. When you measure 55 centimeter, anyway you can't use vernier and the screw gauge. So it has to be meter ruler. Thickness T. Thickness T. How much is that? 3 millimeter. Again, micrometer screw gauge it has to be. Micrometer screw gauge. Okay. Next. What experimental procedure would you follow to obtain a better value for the thickness of a disc? Right, to obtain a better value for the thickness of the disc, what you must do is, rather than getting it at one place, get it at multiple places and get the average. That will give you a more accurate value for the thickness. Let's say obtain or measure, let's say. Measure the thickness at multiple places of the disc. And Get the average. Get the average. The thickness of the certain type of polythene sheet is much smaller than least count of the micrometer screw gauge. Propose a method to estimate the thickness of sheet using micrometer screw gauge. You remember, I explained when you want to get the thickness of paper, what do we do? I said either you can collect a certain number of papers, say 20, 30 papers, put them together, measure the thickness and get the average. Or else, if you have only one paper, fold it multiple times so that you get many layers of paper. All the layers together, you put it into the measurement, get the thickness and divide by number of layers you had. So here, since it's a polythene, we can go for the folding option, right? We don't know whether they have given us enough number of polythene sheets. So we'll go for the folding option. What shall we say here? Fold it into multiple layers and measure the thickness of a certain number of layers and find the average. Clear? So that's not a new question. That is something we already know. Right? When you are very thin paper or blade or something, this is one option for you. Adding multiple pieces and getting the reading. Clear? Alright. So that's all regarding micrometer screw gauge, the past paper questions we had. I explained you the theory, then I did the experiment. I explained there again, how to find the measurements. And then regarding micrometer screw gauge, whatever the past paper structured essay type questions I have taken and I have discussed that for you. Right? Practice all this with the knowledge of all this. Facing any question that you get in this section will be easy for you. Clear? So that's the practical number 2 we are finishing. Next we are going to see spherometer, another measuring instrument we have, spherometer, that we will see in the next experiment.